Assalamualaikum warahmatullahi wabarakatuh. Today we will presenting chapter 5 CHM131, which is about gases. In this video, we will discuss the learning outcome of this chapter, including the calculating gas pressure, understanding the ideal gas law such as Boyle's law, Charles' law, Galileo's law, and the Avogadro law. We will also explain the general properties of gases and the unit of pressure. This topic is important because the gases play an important role in our daily life. Let's begin our presentation.
Hi everyone, today I am going to explain Boyle's law and Charles' law, which describe the behavior of gases. I will explain the Boyle's law first. First, let's talk about the Boyle's law. Boyle's law states that when the temperature is constant, the pressure of gas is inversely proportional to its volume. This means when pressure increases, the volume is decreased, and then when the pressure decreases, the volume increases. In other words, if we squeeze a gas into a smaller space, the pressure becomes higher. For example, when we press a syringe while blocking the tip, the volume of air inside decreases and the pressure increases. And then the formula for Boyle's law is P1V1 equal to P2V2. The P is for the pressure and the V is for the volume. Okay, after explaining the Boyle's law, we'll move to the Charles' law. Next, let's look at Charles' law. Charles' law states that when the pressure is constant, the volume of a gas is directly proportional to its temperature. This means when the temperature increases, the volume increases, and then when the temperature is decreases, the volume decreases. For example, when a balloon is heated, it expands because the gas particle move faster and take up more space. And the formula for the Charles' law is V1 over T1 equal to V2 over T2. So the V same for the volume and the T is for the temperature. The temperature must be measured in Kelvin. So guys, the conclusion is nothing. Oh, I have the easy way to remember for the Boyle's law and Charles' law. For the Boyle's law, squeeze equal to pressure goes up, and the Charles' law is heat equal to expansion. So that's all from me, and now I'll give it to my friend.
In this part of the video, we will explain Graham's law under the gaseous state. Mathematically, Graham's law is expressed as rate is proportional to 1 over the square root of molar mass. This shows Graham's law of diffusion.
Oh my god! Wow!
In conclusion, conclusion, Graham's law explained that lighter gases diffuse and effuse faster than heavier gases due to their lower molar mass. In this part of the video, Avogadro law will be explained. Avogadro law states that at constant temperature and pressure, the volume of the gas is directly proportional to the number of moles of gas present. Mathematically, Avogadro law is expressed as V is proportional to N. In this scene, the balloon is blown 3 times. And now, the balloon is blown 6 times. In conclusion, Avogadro law explains that increasing the amount of gas increases its volume when temperature and pressure are constant.
Okay, now I will explain the Dalton's law. Dalton's law states that the total pressure of a mixture of the gas is equal to the sum of the partial pressure of each gas. The formula is P total equal P1 plus P2 plus P3 plus P4 plus. Okay, for the example, if gas A has a pressure of 300 mm Hg and gas B has a pressure for 400 mm Hg, the total pressure will be 700 mm Hg. So we can also calculate the partial pressure using the mole fraction. Mole fraction is the ratio of the number of mole of one gas to the total number of mole. So the formula is Pa equal Xa times P total.
And now we moving on to division-drum ideal gas behavior. Kinetic molecular theory has 5 basic assumptions that apply to gases. Real gas deviation from the ideal gas model. What you can see here is the picture of ideal gas. The assumption of the ideal gas is particles have negligible volume, particles have no intermolecular force. And this behavior described by PV equals to nRT. In reality, gas is look like this. Real gas are particle has negligible volume, particles have intermolecular force, and at most conditions we can use PV equals to nRT. But it's less valid at high pressure and low temperatures. This is a graph of deviation from ideal behavior of gases. This is what happens when ideal gas and real gas in high pressure. Particles volume in ideal gas are still negligible compared to size of container. particles volume in your gas is now significant compared to size of container. Particles are very close to intermolecular force becomes significant. On the low temperature, ideal gas are decreased in kinetic energy has no impact on intermolecular force. Real gas on the low pressure are decreased in kinetic energy means intermolecular force becomes significant.